In this video, we're going to do a side-by-side comparison of the two approximation methods that we've talked about so that we can really see their similarities and their differences. So first of all, we're going to approximate square root of 48. It's the similar kind of function that we worked with before for square root of 2, but for a different number. So for linear approximation, the very first step is the fact that we're going to be approximating the function y equals root x near x equals 48. So at x equals 48. So that is the function that I'm going to draw, and that is the function that I'm then going to analyze. So sketching a quick picture here, remember that square root is a sideways parabola. Whoops, it starts at 0. So sideways parabola like this. So the point that I'm interested in is 48, and then its y coordinate is square root of 48. Okay. So in the linear approximation, I need to construct a tangent line somewhere close to this point and then compute the y value on that tangent line for x equals 48. Now, nice point will be near 48, where I will be able to, in fact, compute the function value exactly. So what point near 48 is there where I can compute the square root of as an actual number without having to use a calculator and without any kind of decimal approximation? Well, 49 is pretty close to 48, and square root of 49 is 7. So that is going to be my nice point of choice here. Now, I'm not drawing to scale because otherwise it would be way too small. So the method will say at 49, we're going to build ourselves a tangent line and then compute on that tangent line the point that corresponds to 48. And that is going to be our approximation. So this is going to be my approximation here, whereas the corresponding point on the actual curve is the exact value. Okay, so now pause the video here for a second and write down the equation of the tangent line to the curve root x at 49, and then plug in x equals 48 into it here. Okay, so this is what you should have gotten. Notice that again, we're using our general equation for the line, but in order for us to be able to plug things in, I also have to compute the derivative of my function at the point. So here's where I am using 49 as the point where I'm computing the equation of the line at. And only once I've done that am I going to plug in x equals 48 in order to find the approximate y value. Okay, and so you should get something like this, 7 minus 1/14, which is approximately 6.92. Again, the graph here emphasizes the fact that the approximation that you've ended up with is an over approximation because this point lies above where the point on the function does. For Newton's method, the very first step is to take the corresponding value that you're trying to approximate and turn that into a function for whom this is the x-intercept. So I'm going to square both sides first of all, and then move everything over to one side. And now I've taken my value that I'm trying to approximate and turned it into a function f of x whose solution, whose x-intercept I'm actually interested in. So here, the graph is going to look completely different because now I'm sketching x squared minus 48, which is of course a parabola that is shifted by 48 units down. So something that looks like this. Let's pretend it's symmetric. This is minus 48, and then the two x-intercepts are square root of 48 and minus square root of 48. So remembering what we talked about earlier, I have to be able to pick the initial value, the initial guess, close enough to the root that I'm trying to approximate, or I might end up approximating something else. Okay, so here I have to think of a number close to root 48. It can be anything. Newton's method is where you would actually be able to use a calculator, but with only subtraction, addition, multiplication, and quotient. no taking actual square roots. So you could pick any decimal around root 48. I'm going to do the calculations by hand, so I'm going to try to pick nicest number available. Root 49, which is 7, is pretty close to root 48, so this is going to be my initial guess here. So this is going to be root of 49, which is 7. So my initial value that I am choosing is going to be 7. Now, the method, again, graphically, constructs the tangent line to my graph at that point, and the x-intercept of that graph is the x1 value. So that's my next best approximation, okay? Now, using the formula that we've derived, the formula claimed that x1 was x naught minus f of x naught over f prime of x naught. So notice too, that here I'm also going to have to compute the derivative of my function. My function is x squared minus 48. So the derivative is just 2x. So then the next step is to actually plug in my value for x naught, which is 7. So the function will be 7 squared minus 48. And the derivative is 2x. So 2 times 7. Calculating that out, I see that I'm getting 7 minus 1/14. Which is approximately 6.92. So notice that my last line of calculations in both of these methods is actually identical. Okay, so yes, they've ended up with the exact same approximation, but for linear approximation, you're done. There's no way to proceed. Linear approximation will only be able to produce one value, and that's it, you're done here. With Newton's method, this is the first value it produces, and I can feed this value through the algorithm again in order for me to get a better approximation of root of 48 still. So please take a look at these methods side by side so you can really see how the setups are quite different, even though the ultimate goal of approximation is the same.